This is lecture number 5 in discrete optimization, which could as well be called the Edmonds Festival, because this lecture is about Edmonds' algorithm for computing matchings in general graphs. So here's a brief overview of the lecture. We start by talking about so-called augmenting paths. Now, no longer flow augmenting paths, but matching augmenting paths. We need a sort of data structure which we call alternating trees. Then we can explain a generic augmenting path algorithm, which does actually solve the problem for specific graph classes, for example, bipartite graphs. And finally, we turn to Edmonds' algorithm to really compute matchings in arbitrary, also non-bipartite graphs. So why did I say the lecture could as well be called the Edmonds Festival? Well, because the matching problem is very tied to the name of Jack Edmonds, actually. And his paper, which was back in '65 titled Path, Trees, and Flowers, was extremely influential. That was the paper where he claimed to have an efficient algorithm, so a polynomial time algorithm to solve the matching problem in general graphs. And just to give one example, this book here that you see on the slide, that is a collection of papers both by Jack Edmonds but also other researchers, which was edited on the occasion of a workshop in Auxerre in France to celebrate the contribution that Jack Edmonds actually had on the area discrete optimization. But not only Jack Edmonds is a name that pops up when you think about matchings. Another name or two names that actually pop up when talking about matchings are those by Roth and Shapley. And as you might know, about 80 years ago, the Nobel Prize in Economics was awarded to these two researchers for their work on the theory of stable allocations and the practice of market design. And stable allocations is actually stable matchings. So that's a definition that we are not going to look at in this course. So if you're interested in that, you should take a course in game theory instead. So let's go ahead. What is the definition of a matching in a graph? So a matching in a graph, you already know that in an undirected graph, that's just a subset of the edges such that no two edges share a common endpoint. So when they intersect the vertices of these two edges here, then they do not share a common endpoint. Okay. With a given matching, so this given blue matching here, we call a node free if it is not incident with any matching edge, and we call a matching perfect if every node in the graph is actually matched. So in this example, this would be a free node because it's not incident with any of the blue matching edges, and so is this one. And the matching is obviously not a perfect matching because there is free nodes, and therefore not every node is matched. The combinatorial problem, the optimization problem that we want to solve, is to find a matching of maximum size. We could also generalize, so this is the definition. Given an undirected graph, an arbitrary undirected graph, compute me a matching, so a subset of the edges of maximum cardinality. We could as well look at the problem where the edges of the graph have weights, and then we would like to maximize the total weight of the given matching. That can also be done, but for simplicity of exposition, I just restrict to the cardinality version of the matching problem for this lecture. Notice that, or remember that, matchings as a subset of the edges of a graph, that is not a matroid, and therefore we cannot use the greedy algorithm to compute matchings. We actually can use the greedy algorithm to compute matchings, but it will generally not give us a maximum size matching in the graph. And you can come up with easy examples to show that yourselves, I hope. Later in this course, we will be looking at the greedy algorithm for matchings, and we will show that the greedy algorithm at least gives us a so-called 2 approximation. So if I just greedily select edges of the graph until I cannot augment the matching anymore, then the matching that I get is at least as large as half the size of the optimal or maximal matching. For everything that we will do in this lecture, we need the notion of the symmetric difference of subsets of the edges of the graph. So given two subsets S and T, subsets of the edges of the graph, this S triangle T denotes the symmetric difference. So it's all the edges which are in S but not in T, together with all the edges which are in T but not in S. So here is a little example. So we have a subset of the edges S in blue on the left-hand side, which is actually matching. We have a subset of the edges T on the graph in the middle here, consisting of these three red edges. And then the symmetric difference would be all the edges which are either in S but not in T. So that would be this edge up here, or in T but not in S. So that would be this edge and this edge. Okay, so that the symmetric difference consists of these three edges over there. In computing matchings, we will be working with so-called augmenting paths again. So let us make the corresponding definitions. First of all, a path P in the graph is called M alternating for the given matching M if the edges of P are alternating between edges from M and non-edges of M. Okay, so that would be an alternating path where we alternate between blue matching edges and non-matching edges. And we call such a path M augmenting. So an M augmenting path is just an M alternating path where the terminal, or the start and the terminal node are actually free with respect to the matching M. So the first and the last node of this alternating path are non-matched vertices. By definition, an M augmenting path must have an odd number of edges. That is because we alternate between matching and non-matching edges, and the first and the last edge on this augmenting path must be non-matching edges, right? Now, thinking algorithmically, if we are given some matching M, we can augment this matching M along an augmenting path P. Okay, so that just means I use this augmenting path P to increase the size of the matching by exactly 1. And how do I do that? Well, I just flip the roles of matching and non-matching edges on this alternating path. Okay, so I make every non-matching edge on P, I make it a matching edge and vice versa. So formally, that just means I define a new matching M prime by taking the symmetric difference of M and this alternating or M alternating path. So here's a little example. We have a blue matching here on the left-hand side, M, and here we have an M augmenting path, right? Because it alternates between matching and non-matching edges, and the two endpoints of this path are actually free because they are not matched. And now we can just flip the roles of matching and non-matching edges on this M alternating path in order to obtain a matching which has size 3, so one larger than the original matching. As a matter of fact, when we do that, so we are augmenting the matching M by using this M augmenting path here, everything that was matched before in M, so that is these 4 vertices here, will still be matched in the new matching M prime, right? So if I have vertices which are matched in M, this is going to be an invariant, so it's still going to be matched after I have augmented the matching using this alternating or augmenting path, right? So here on this picture, that is the green vertices on the left, which were the matched vertices for M. And these green vertices are still matched only by different edges on the right-hand side in M prime. So obviously, if we still have an M augmenting path in the graph for a given matching M, that matching cannot be a maximum size matching because we can still use this augmenting path and we have one more matching edge, right? But is the reverse also true? And the answer is yes. So if there is no more augmenting path, it's really just like with flows, then the matching is already a maximum size matching. Okay, so that's a theorem that was already proved by Berge in the 50s, and it's the characterization of matchings by M augmenting paths. So a matching is a maximum size matching if and only if there is no M augmenting path anymore. One direction we already proved, so the only if direction is already proved, because if we have a matching M and there still is an M augmenting path, then that matching was not maximal, right? Because we can augment the matching, we can increase its size by 1 by just using this M augmenting path and obtain a matching of size M plus 1. So it's a necessary condition that there is no M augmenting path anymore, but is it also a sufficient condition? And the answer is yes. So let's quickly see why this is true. So we take a matching M, which is not a maximum matching. So there exists a matching of a larger cardinality. And we show that if that is the case, there still exists an M augmenting path in the graph. And that is the proof of Berge's theorem. Okay, so let M star be a maximum size matching in the graph. And what we do is we consider the symmetric difference. So we look at the graph G prime, where the edge set is exactly the symmetric difference of these two matchings M and M star. So containing all the edges that are only exclusively in M and only exclusively in M star. Now notice that we have eliminated the edges that are shared by both matchings M and M star. And by doing that, we have eliminated the same number of edges from M and M star. And now let's look at the graph G prime. How does it look like? Because N and M star are actually matchings, the maximum degree in either of them, in M and M star, that is 1, right? So each vertex can be matched at most once in either of the two matchings. So if I take the edges which are contained in either M or M star, then the maximum degree of any vertex can be at most 2. So it could be incident with a matching edge from M and with a matching edge from M star, but not more. So that means that the maximum degree in this graph G prime of any vertex is actually 2. So what kind of graph is that actually? Let's have a look. So we have M star, the maximum matching, which has assumed more edges than our matching M in blue. We look at the symmetric difference of M and M star, and I just explained that all the vertices of the graph have maximum degree 2. So that could be either paths, right? So where the degree 2 is at the intermediate nodes of a path and degree 1 at the ends of the path. It could be isolated nodes. That would be nodes which are not matched in either of the two matchings. And this graph could also contain cycles. But since both M and M star are matchings, these cycles must have even length and contain the same number of red and blue edges. Now, since we assume that M star is the larger matching, how can M star have more edges? Remember that by taking the symmetric difference, we have removed the same number of edges from both M and M star. So M star can have more matches only if it contains at least one more edge in these paths. And that exactly means that we will have one path, which will actually be an M augmenting path for the blue matching. And that's exactly what we were looking for, an M augmenting path that still exists. So here is the argument in writing. So all the nodes have degree at most 2, therefore this graph G prime contains isolated nodes, paths, and cycles. And the edges always alternate between matching and non-matching edges for the paths and the cycles. And since M star actually has at least one edge more, this graph G prime must, so M star is larger than M, this graph G prime must contain a path with more edges from M star. That was the red matching in the picture. And such a path is then, by definition, an M augmenting path. So we have shown the existence of an M augmenting path, which is what we wanted to show. Okay, so we have a maximum size matching in the graph if and only if there is no M augmenting path in this graph. So here is again another illustration. The blue matching has size 2. The matching M star, which happens to be a perfect matching for that graph, has size 3. And here, if I take the symmetric difference itself will be exactly this M augmenting path for the matching M. And I can use this M augmenting path and would be flipping the roles of red and blue and obtain a larger matching. So the algorithmic task that we actually have is we have to be able to find these M augmenting paths. So given an arbitrary matching, how do we find an M augmenting path? And that is what will be done by using so-called alternating trees. So having Bayes' theorem characterization of maximum size matchings, we exactly know how we want to compute such matchings. And the generic algorithm is just exactly like for maximum flows actually. So we start with the empty matching, and we know that we have to, as long as we find M augmenting paths, we are not optimal, so we can still continue, and that's what we do. So while there exists an M augmenting path P, we use it to augment the matching by exactly one edge. So the only question really is how to find these augmenting paths in the current, with respect to the current matching. And conceptually, the idea is actually quite simple. The first thing to realize is that we have to start our search at an unmatched node, at a free node. Okay, so the situation looks as follows. We say pick an arbitrary unmatched node R, and essentially what we now do is just a breadth first search to scan the whole neighborhood of R and scanning all the neighbors of R, etc., in the hope that then eventually we will find this M augmenting path. Okay. In comparison to the breadth first search algorithm, where we always scan the whole neighborhood, we only have to be a little bit more careful, because actually we are not interested in any path from this node to that free node, but we are only interested in M alternating paths. So we only want to find this one. So that is the little twist that we have to add to the breadth first search algorithm in order to make sure that all the paths from R, starting from R, will exactly represent alternating paths and not just any path. And to that end, we use the idea of so-called alternating trees. So the idea here is as follows. We always start at the node R, which is called the root, which is an unmatched node. Notice that when no unmatched node exists anymore, we can stop because we will have computed a perfect matching. Now, if any of these three nodes here would be unmatched as well, we would be done as well, because we will have found, for example, an augmenting path consisting of only a single edge. So what we actually know is that, or assume, is that all these three nodes are matched somehow. And this way we can extend this alternating tree in a unique way. And then we continue with this procedure. And by doing so, the tree will represent alternating paths from starting from the root node, which is a free node. And it actually classifies the nodes on the way into nodes that have an even distance from the root node and an odd distance from the root node, like in this picture. So here, these neighbors of the root node would have an odd distance, namely distance 1 from the root node. Then the next nodes, that is the unique nodes, because this is unique matching edges. They have an even distance, and then again an odd distance, and so on. Notice that this vertex here of degree 3 in the tree can only happen at a node with an even distance, because otherwise there is always a unique matching edge to continue the construction. And well, as soon as we find another free node, we will have found an augmenting path. And that is the idea, and that is what we are looking for. So we build this tree inductively. Initially, it only consists of the root node itself, and remember that is a free node. And then assume we have already computed a partial tree T. We always try to extend this partial tree and connect it to a yet unconnected node V, which again will be a node that is matched. So then we know how to continue with this unique matching edge. And if this would be a free node, then we will have found this M augmenting path actually. So here we have an operation which says that we extend this tree by selecting this edge here, which connects U to V. V is outside T, and it also connects the unique matching edge to the tree. So here's the description of this extension operation, extending the tree using an edge UV. So what kind of edge from the graph do we actually choose? Well, we scan the neighborhood of U for vertices V which are not yet connected to the tree. And as I said, if this would be a free vertex, we would have found an M augmenting path, and otherwise this will not be a free vertex and it will be matched to some other edge. So then we would add these two edges to the tree. This edge here must have had an even distance from the root node. This will have an odd distance, and this again will have an even distance from the root node. So once we have done that for these two edges here, we can just iterate the whole thing. So that would mean selecting an arbitrary node here from the tree T. Well, actually now this is the whole tree T here, which has an even distance from the root node. And we again scan the neighborhood of that node for yet unconnected vertices in its neighborhood. And we just iterate this procedure. So here is another illustration of the same thing, where actually these two edges would be added to the tree using this extend tree operation. Of course, what we are looking for is M augmenting paths. So as soon as we find in the neighborhood of a node U, and remember that was an arbitrary node that we selected from the tree here, which currently has an even distance from the root, so any set from the set X, as soon as we find in its neighborhood a yet unmatched vertex V, we will have found an M augmenting path. And that is what we have been looking for, M augmenting paths, in this case, this path from the root node to the free vertex V that we potentially have found. Now, this already gives us an algorithm, so we now have a way of finding M augmenting paths by computing these alternating trees. So that is not so difficult. So we actually end up at a very generic augmenting path algorithm, of which we will see that it works for certain graph classes, for example, bipartite graphs. But unfortunately, it does not yet work in general, because in fact, we might overlook some M augmenting paths. But first, let us have a look how this augmenting path algorithm, this generic augmenting path algorithm actually works, even though it does not function for arbitrary graphs yet, because it's actually kind of cute and also non-trivial. Okay, so as usual, we start by initializing with an empty matching, and then we iterate, we go through this for loop for all the vertices of the graph. And the way to think about this is that all these vertices, which are called R for a reason, are considered to be root nodes of an alternating tree. Okay, so we pick such a vertex R. If this vertex R has been matched before in an earlier iteration, we of course continue, we skip it. So if it's not yet matched, we start building up the alternating tree. We start building up the alternating tree by picking the root node as the starting node. And here are all the conditions in order to extend this tree by an additional edge from U to V. Now, two things can happen in each of these iterations of this while loop. Either we find that the vertex V is a free vertex, and remember that means that we will have found an augmenting path for the current matching M. So, and then we just use it and we augment the matching M. the important thing to realize at this point in time is, since we're having an augmenting path which started at R, when this happens, then vertex R has been matched. Okay. So if we do not find an augmenting path, we just extend the tree using the operation that I explained before. So that means the edge from U to V is added to the current tree T, plus also the edge, the matching edge that goes out of V, this unique matching edge. All right, so that means we could iterate through this while loop and building up the whole alternating tree, and it could end also without being able to find any augmenting path. So that means we eventually have refuted this vertex R as a potential vertex that might be matched, and we iterate, or we go to the next vertex. Okay, so that means when that happens, so when we are building up the whole alternating tree without finding an augmenting path for the matching, that means that vertex R will remain unmatched, at least in this iteration. Now let us collect some observations about this matching algorithm. So one thing is clear: whenever this extend tree finds an augmenting path that is rooted at R, there also exists an M augmenting path because we just have found it, right? So this is how we constructed the alternating tree. The more relevant question, of course, is what happens if extend tree fails to find an augmenting path rooted at R? Can we be sure that this is okay? Is it really okay to skip vertex R at that point in time? Because it could mean that also at the end of the algorithm, vertex R is left unmatched. So that question is still open. Could we possibly miss some of the augmenting paths in the graph? And there is a positive and a negative answer to that question. So let me first start with a positive answer to that question. So that's answer number one here. I call it the augmenting path lemma. And read carefully what it says. It says the following: suppose there is no M augmenting path rooted at an unmatched vertex R. So here I write there does not exist an M augmenting path rooted at an unmatched vertex R. Then there exists a maximum matching for the whole graph M star, where this vertex R is also unmatched. So if there doesn't exist an M augmenting path for the given matching M rooted at R, we can also skip it. So it could still be that there exists such an M augmenting path rooted at an unmatched vertex R, and our algorithm doesn't find it. So this lemma is about the situation where it actually doesn't exist. And the claim is that when it doesn't exist, we can as well skip it. So we are not blocked in some way by the matching that we have pre-computed in earlier iterations. Let us look at the proof of this augmenting path lemma first. So here I just repeat the statement. So given some fixed matching M in blue here, and suppose we happen to know that there doesn't exist any M augmenting path starting or ending at this root vertex R, then we can as well skip it, because then I claim that there exists some other maximum matching M star in which R is also unmatched. So our continuing our computation without R would be okay. So we pick a maximum size matching in the graph, and let us assume that vertex R is actually matched in M star, and then we have to show that there exists another optimal maximum size matching in which R is actually unmatched. Okay. So what we do is we look at the symmetric difference of M star and M. So we have these two matchings. M, that is the one that we started with, and M star is a maximum size matching. And I claim that there exists an even length path in this symmetric difference, which I call G prime here. Okay, so there exists an even length path P, which actually contains this vertex R, this root vertex R. So first of all, because this vertex R is actually currently unmatched in M, in the symmetric difference, but it is matched in M star, in the symmetric difference, it will be incident with a green edge. A green edge is from the matching M star. And still, because R is unmatched in M, if I continue this path here, it cannot end up in a cycle, because that would mean R would be also matched in M. So also because R is unmatched in the blue matching M, this is going to be a path, and it's even going to be an even length path, because otherwise, suppose not, then that would actually mean we have a green edge here at the end, and that would be an M augmenting path containing this root vertex R, which we assumed doesn't exist. So I actually have this even length path containing R because of two reasons. Because R is unmatched in M, and because there exists no M augmenting path from R. But now, having this even length path containing R, let us take a look at the matching M star, because in M star, currently this vertex R is matched, right? Because this is a green edge here. We have an even length path here. So, but that means in the symmetric difference, but that means we could just as well flip the roles of blue and green here. And that exactly means that we take M star and take the symmetric difference with this even length path P. And that's a matching that has still the same size. So that is a matching with the same size as M star itself, right? Because it's an even length path. So we still have the same number of green edges after this operation. And actually R is unmatched in this new matching. And that is what we wanted to show, because we wanted to show that there exists another maximum or some maximum size matching M star where R is unmatched, and we have just found it. And so once again, what does this give us? Going back to the slide. So this tells us that if there really is no M augmenting path rooted at R, then in the algorithm that we are considering with the current matching M that we have pre-computed, it's totally okay to discard this node R and skip it when there is no M augmenting path rooted at R. So in the case of non-existence of an M augmenting path, we are safe. Our algorithm is well defined. The trouble is that non-existence of this path does not always coincide with the fact or the question if we actually find it with our algorithm. So the truth is, and that is answer number 2 to this question, that our algorithm might fail to find M augmenting paths. So if there exists an M augmenting path, our algorithm nevertheless quits this while loop without having found this augmenting path. And let us see how this can happen. And that has to do with odd length cycles. So suppose we start building up the tree from R, like here. We have added vertex X and the corresponding matching edge. And then we have added this one, and at a later point together with this matching edge. And then we had added the edge from B to Q together with that corresponding matching edge after that. Then we see that this edge UV, which is an edge from the graph, can no longer or cannot be added, because U would be an edge from which we like to extend, but V is already in our tree. Okay, so that is not allowed. And moreover, this edge from P to Z here is also not added, because we are extending the tree only from vertices which have an even length distance from the root vertex, right? 1, 2, 3, 4. So this one has an odd distance from the root vertex, and we are not extending the tree from these vertices. Now you might say, okay, so why don't we do that? Why couldn't we just extend the tree also here? But remember that we want to find alternating paths, right? So if I follow this path now, it's no longer going to be alternating. So this doesn't work. So that means this edge is not going to be added, neither this edge is going to be added, and we fail to find an augmenting path which exists in the graph, which is this path here. That's an augmenting path. Another observation with odd length cycles is the following. Not only may we fail to find this augmenting path, it is actually also possible that the vertices on this odd length cycle are classified in different ways depending on in which order we are processing the edges of the graph. So let's suppose we are first processing this edge here. So then this one gets an odd length distance from the root, and then this one an even length distance. Suppose now we consider this edge from U to V. So this vertex V will again have an odd length distance, and this one will have an even length distance. Okay. So Q has in this case an even length distance from the root, whereas when we first consider this edge from B to Q, then this one would get an odd length distance. So it would be classified in these sets X and Y in different ways, depending on in which order we are processing these outgoing edges from B. And that is also kind of annoying. As a matter of fact, this is exactly the problem that we are coming across with odd length cycles, because when this classification into even and odd length distances is uniquely defined independent of the order in which I process the edges of the graph, then everything works out nicely. Okay, so that is what I call here the unique label property. I call a graph, or I say a graph has this unique label property if this extend tree procedure uniquely classifies all the vertices of the graph to either odd or even length distances from the root node, and that irrespective of the order in which the nodes and edges are actually examined by the algorithm. And once this unique label property holds for a given graph, our algorithm also works. Okay, so that's the next lemma. Suppose we have a graph that satisfies this unique label property. Then if there exists an M-augmenting path, then our algorithm also finds it. And the proof is quite simple. So here is again the repetition of the statement. If our graph has this unique label property and there exists an augmenting path, then our algorithm finds it, in short. Okay, so let us just pick some augmenting path starting at a root vertex R, ending at a vertex V here. So that's some augmenting path for a given matching M, computed by our algorithm. So we assume there exists an augmenting path, and that is the one, or one of them. Since this path is an augmenting path, the length of this path is odd. And as a matter of fact, our algorithm must put this vertex U, which is the second to last vertex on this augmenting path, must put it in the correct distance classifier. That was the even distance actually from the root node. And that's simply because there exists this path, which in total has an odd length. So U has on this path an even length from the root vertex. And the unique label property says that these labels are uniquely defined, independent on which order I process edges and vertices of the graph. So this vertex U will be classified correctly as an even distance vertex from the root vertex, and therefore extending the tree with this last edge from U to V is an eligible action for the algorithm, and hence the algorithm will find this augmenting path P. So if our graph has a unique label property, our algorithm will find all the existing augmenting paths. So that's nice. So the question now is, are there interesting graph classes which actually do have this unique label property? Or is this just a definition that we made because it was convenient for our algorithm? The answer is yes. There is a very rich class of graphs for which this unique label property is fulfilled, and that is bipartite graphs. Oops. Bipartite graphs, if you remember, that's graphs where the set of vertices can be partitioned into two subsets, A and B, and all the edges go between the sets A and B, and there is no single edge which lies inside any of these subsets of vertices. What do have bipartite graphs to do with our unique label property and with the existence of of odd length cycles? And the answer is, well, first of all, bipartite graphs satisfy the unique label property. And the proof goes by showing that bipartite graphs are exactly characterized by the fact that they do not have odd length cycles. Let us quickly see why this is true. So we have a bipartite graph that is what we want to show if and only if this graph has no odd length cycle. So the forward direction, so this direction is the simplest one. If we want to have a cycle at all, we have to start at some start vertex v0 here. And in order to come back to v0, we have to use an even number of edges, right? So any cycle must have an even number of edges because we have to return into the set A. So that was the simple direction. And the other direction, so if we have a graph without odd length cycles, I have to convince you that there must exist a bipartition of the graph so that I can recognize the graph as a bipartite graph. Also, that is not too difficult. So I pick again a vertex v0 arbitrarily, and I define these two subsets A and B for the bipartition as those vertices which have an even distance from v0, that is A, and B is defined as those vertices with an odd distance from v0. Okay, so here this d of v refers to the length of a shortest path in terms of the number of edges. Now, why is this going to be a valid bipartition? Let us consider the algorithm that actually computes these shortest path distances in terms of the number of edges, and that is exactly breadth first search. So we start with our start vertex v0, and then there is a couple of vertices of distance 1 from that start vertex, and that is the neighbors of the start vertex. So they have distance 1. Then there is a set of vertices which are neighbors of neighbors, but which are not connected directly to the start vertex, neighbors of these neighbors, etc., etc. So in my picture, I have distances 1, 2, 3, and 4 from the start vertex v0. And by definition of breadth first search, we know that such shortcut edges do not exist, because that would mean that this vertex would have been classified incorrectly since it's a direct neighbor from a vertex here. And this is not the case. Moreover, also vertices inside these subsets cannot exist. Why is that? Well, that's because we assume our graph has no odd length cycle. And if I had such a vertex here, that would give me immediately an odd length cycle. And therefore, putting all the even length or even distance vertices into A, so that would be this one, this one, this one, and the other ones into B, indeed gives me a valid bipartition of the graph, such that all the edges go from vertices from A to B, but not within A or within B. So that finishes the proof of our characterization of bipartite graphs. Okay, nice. We have characterized bipartite graphs as exactly those graphs which do not have an odd length cycle. But what has this to do with the unique label property? Well, as a matter of fact, the non-existence of odd length cycles will imply that the unique label property must be fulfilled. And why is that? Well, the number of edges on any path from the root vertex R to U, so on any RU path P, must be either even for all such paths, or it must be odd for all such paths. Because if I had a path of even length from R to U and another path of odd length from R to U, that would give me a negative length cycle. But negative length cycles do not exist in bipartite graphs. Hence, any path has always the same parity, so even or odd, in terms of the number of edges, and therefore our algorithm will always classify the vertices of the graph into even or odd length distances, independent of which path which order of the edges and which path was considered first. And as a consequence, that gives us the first theorem, at least for our matching algorithm, our generic matching algorithm. And that's this theorem. So the augmenting path algorithm that I had on the earlier slide really computes a maximum matching in bipartite graphs in that computation time order n times m. Let me say a word about the computation time on the next slide. So the claim is that the computation time of our matching algorithm is order n times m, n number of vertices and m number of edges of the graph. And why is that? Remember what the algorithm does in the outer loop. We are going through all the possible vertices of the graph, which we consider as possible root nodes of an alternating tree. So that's at most n vertices that we are considering. And for each of these vertices, or for each of these roots R, we are constructing such an alternating tree. Okay, so the construction of this alternating tree is essentially a breadth first search algorithm with a little more checks and balances, but that doesn't really go into the computation time. So that's only additional constant time operations. So therefore, the construction of this alternating tree takes order n time, each of them. Okay. Once we have found an augmenting path for the current matching, so we possibly have to compute or have to update the corresponding matching, but that takes linear time in the number of edges contained in the matching, which is at most order n. So all this together, that would be order m plus order n, so that is still upper bounded by the number of edges of the graph. So we have n such for loops, and each of these for loops is construction essentially of a breadth first search tree, and so that gives us the computation time that I claimed, order n times m. So we have a first solid statement about our generic matching algorithm, which computes optimum or maximum size matchings in bipartite graphs in polynomial time. And then the final part of the lecture is going to treat the case when we have arbitrary, so also non-bipartite graphs. So how do we treat these odd length cycles? And that is exactly the contribution of Jack Edmonds' paper from 1965, in which he, for the first time, gave a polynomial time algorithm to compute matchings in general graphs, so not only bipartite graphs. So let us recall the algorithm, which we still have to fix for these odd length cycles. So the algorithm was as follows. It was going through all the vertices of the graph and trying to match these vertices, so this particular fixed vertex R as a root, by computing in this while loop here, by computing the corresponding alternating tree. And if we are lucky, we match this vertex. And if we are unlucky, or if it's not possible to match this vertex, we skip it. And the trouble was that for a particular given root vertex, we might actually fail to find an augmenting path for this R because of the presence of these odd length cycles. So what do we do with these odd length cycles? And there is actually an anecdote about that that Jack Edmonds liked to tell in one of these workshops that I attended in Ossois in France. So he said that he was invited to talk on a combinatorics conference, but he actually had no new result and he didn't know what to talk about. And the evening before it was his turn to give a talk, he was sitting and wondering, what the hell can I talk about? And during that evening, he was coming up with the idea that I'm going to explain to you right now. So how should we care about these odd length cycles? Because remember, when we have the presence of an odd length cycle in the graph, we might miss an augmenting path. For example, when there would be another edge here, right? We could overlook this augmenting path in the graph, and that means that our previous algorithm doesn't find an augmenting path for a given root vertex R, even though there is one. And Jack Edmonds' idea was the following. He calls this structure that we see here, he calls it a flower. Okay, so this flower has a stem. We are always starting building this alternating tree from the root node, and there is a base of this flower. So there is the stem, there is the base, and there is a blossom. So the odd length cycle is called a blossom. So here we are looking at an odd length cycle of total length 5. There could be blossoms of other sizes too. Obviously only odd lengths of cycles could be potentially blossoms, but they could have sizes 3, 7, 9, and so on. And I think it's good to look at least 2 more examples to see what could be going on in a blossom, because otherwise maybe this particular picture is over-intuitive. So for instance, we might have blossoms of size 3 even. So that happens when our root vertex is the blossom itself. It's okay, so we start looking for an augmenting path starting from this root vertex here. We find a neighbor which is matched. Okay, so we continue and then we find the existence of this edge backwards to the root. And well, if I just draw this in a different way, we see that we have exactly a blossom of size 3. So it's an odd length cycle and it contains precisely 1 matching edge. So if we go back, we see also that we have here an odd length cycle of length 5, and it contains precisely 2 matching edges, which, by the way, is also the maximum number of matching edges that could be present in an odd length cycle. Okay, so we have one potential blossom of size 3 that could happen, and larger sizes are possible as well. So down here we find a stem of a non-trivial length, and we find an odd length cycle here, because, for instance, when fanning out from this vertex Y, we found 2 neighbors which were already matched. So that was W and P here, and B had 1 more neighbor up here, but that one was already part of the tree. So we continue searching from that vertex A here. So we find yet another matched neighbor C, and then there is an edge backwards towards one of the nodes, which has even distance from the root. And here we have our odd length cycle of length 7. And notice that within such an odd length cycle, the graph could have potentially more edges that were not considered, are not part of the alternating tree, simply because of the order in which we are processing them. Now, so far, this is just a definition and doesn't help. But one of the observations that I kind of already indicated before is that when I have such an odd length cycle, when I have such a blossom, it can only have as many matching edges as the length. I mean, the maximum number of matching edges is determined by the length of the cycle. So for a blossom of length 5, at most 2 matching edges. If I have a blossom which consists of an odd length cycle of length 7, at most 3 matching edges, and so on and so on. So, and there is no way of getting more into such an odd length cycle. So, because these odd length cycles exist, we might miss the augmenting paths. And the brilliant idea that Edmonds had is, oh, come on, I mean, blossoms are making trouble, so I just shrink them. I just eliminate them from the graph. And that's the idea. So when you look at this flower here, the idea is, okay, the odd length cycle seems to be troublesome for my algorithm, so let me just forget about it. Let me just compress all this stuff, not to say all this shit, all this stuff together into one node, one supernode B. Okay, and that's the idea. I just shrink the blossom. And notice that now very nicely we can find our augmenting path in this newly defined graph. So how would that actually help? Let's have a look. Let's suppose we find this augmenting path in the new graph. So we use it, and by doing so, we will match the root vertex that we started with. We will match this vertex. But now, how does this help, or what meaning does this have in the original graph? Well, let's just copy paste the original graph back into this supernode B. And this is how it looks like, right? So I have now just blown up this supernode B into the odd length cycle that it was before. And now observe one thing. I have new matching edges incident with this odd length cycle, whereas in the beginning it was actually this edge from X to B, which was incident with this odd length cycle. Now it is this edge here, which connects Z. But I can, in this odd length cycle, and that's the main point and the most important intuition, I can throw in two other matching edges, namely this one and this one. And I have the same number of edging matches within this odd length cycle, within this blossom, as I had before. But now I have matched one more of the nodes on the outside of this blossom. So when blowing up this blossom B here into its original structure, this larger blossom, this odd length cycle, we are not taking the same matching edges as we had before, but we are guaranteed by the odd length of the cycle that we can at least choose the right number of matching edges as we had before. So we had two before here, we have two inside this odd length cycle there, and the same is true for all odd length cycles. So let me try to explain this intuition once more on this picture. So I have drawn here a slightly more complicated situation, but again, an odd length cycle of length 5, and for a change connected to a couple of other nodes here via some edges, and it also contains an edge which is also called a chord for the cycle, okay? And our algorithm to construct alternating trees has already constructed this part of the tree, and now finds this red edge here from U to V, which actually closes the blossom. And yeah, we know that this causes trouble in finding augmenting paths for the current matching. So we shrink the blossom along this edge UV, which just means I contract everything that sits in the blossom here into this new supernode B. Okay, and I do this example so that you see what is going on. So for instance, this chord of the cycle disappears. These two edges which connect X, they are actually becoming one edge to connect X to the supernode B. And Z and Y are now also directly connected to the same node, the supernode B, while they haven't been connected to the same node here on the odd length cycle. And the crucial insight is for this whole operation, the shrinking of blossoms, is the following. When we shrunk the blossom in this iteration, the whole odd length cycle, the blossom was connected to one matching edge. okay, and precisely one matching edge. That is by definition of this flower. Now, no matter what we do later on, so suppose we use the corresponding augmenting path that we find in this newly defined graph with a supernode B here. Okay, so that would mean we would flip along this augmenting path matching and non-matching edges, and this one would become a matching edge, and this one would not be a matching edge anymore. But in any case, this supernode B will be incident with precisely one matching edge after we have done that, at most one, or precisely one, to be honest. Okay, so the crucial insight is that when we have this blossom B here, so here is an arbitrary odd length cycle which might consist a lot of chords. The situation when we shrink such a blossom, this odd length cycle, we precisely know how many matching edges we have on this odd length cycle, and that is exactly the length of the cycle minus 1 divided by 2. So it would be, if the length of the cycle is 5, it would be 2 matching edges, 7, 3 matching edges, 9, 4 matching edges, and so on. And at the moment that we shrink such a blossom here, we were actually entering with our alternating tree that odd length cycle on a matching edge. So with this green node here. So when I look at it from inside this cycle, that means that with respect to these 3 matching edges inside the cycle, this one is free. So this one can be matched with the outside world, okay? And no matter what happens algorithmically, now we use augmenting paths here. So later on, this matching edge might have disappeared. That is incident with this green node here. And instead, because we were using some augmenting path, we might be using this one, that one, that one, or that one, but only one, right? Because this is going to be a supernode. This is going to be one node. So the whole thing will be matched with at most, or actually precisely, one matching edge to the outside world. And afterwards, when we expand this supernode again into its original cycle, there is always the possibility to make sure, so suppose this one is matched to the outside world, then we can distribute these 3 matching edges inside the cycle in such a way that it is feasible that this one is matched to the outside world. So that is what I say here. There always exists a matching inside this blossom B of the correct size, leaving an arbitrary vertex V from the cycle free, and therefore we can re-expand the blossom later on and can always feasibly extend to the original size of the matching. Okay, so we only shrink blossoms containing a stem or a stem node B and this number of edges, the right number of matching edges, and we afterwards can always be expanded feasibly with the same number of matching edges inside this odd length cycle. So that is hopefully the intuition that you need in order to understand the shrinking business, the blossom shrinking business. Okay, so technically we introduce into the algorithm a new procedure, a new step, which is called shrink blossom using a particular edge that we found. And the precondition is, of course, that has to be an edge of the graph. And both vertices that I have currently an even length distance from the root node. Therefore, this edge is actually closing an odd length cycle. And going backwards, backtracking towards the root, we can actually identify the common ancestor of these 2 nodes, U and V, and thereby identify the whole flower, so the blossom and also the stem. Okay, so the base of the blossom, that is the lowest common ancestor of both U and V in this alternating tree that we have already computed. And then what we do is we shrink the corresponding blossom B, and that is the cycle that contains now this newly added edge from U to V. So that was the edge that was closing the corresponding cycle, and that is now contracted to this supernode B, and we just continue in this iteration of the algorithm to work with this smaller graph, which contains the shrunk blossom and less edges and less vertices as well. In order to make the statements to come a little bit more formal, let us define by G prime the resulting graph that resulted from shrinking a blossom, and M prime would be the restriction of the matching of an arbitrary matching M to the edges of this graph G prime where the blossom has been shrunk. Now, what do we need in order for this to work? We need to prove this little claim here, namely that by shrinking these blossoms, we do not add any augmenting paths that haven't been present before, but we also do not lose any augmenting paths in the graph that have been present before. So losing augmenting paths that have been present in the graph, but we didn't find, that was our problem that we wanted to solve. So that's the main thing. We are now finding these augmenting paths which we didn't find before, but also we should make sure that by shrinking blossoms, we are not creating any new augmenting paths which were not present in the original graph. So that is contained in these two lemmas. So lemma number one is in one direction. Suppose we have an M prime augmenting path P prime that is in the graph that has been shrunk with a shrunk blossom. Then there is also an augmenting path for the same matching, for the corresponding matching in the original graph. And for this part of the lecture, forgive me when I use essentially proofs by picture, because when I write it down in terms of notation, that doesn't really help a lot. Okay, so here is my proof by picture. And remember what we want to do. If we have an augmenting path P prime in the shrunk graph, then we also have an augmenting path P in the original graph. So the first case is the trivial case where the augmenting path is not even incident with a blossom that I shrank. So here is the supernode. So here's the situation where the augmenting path in the graph G prime is not even using the supernode B, then obviously the same augmenting path also exists in the original graph. So there is nothing to prove if the augmenting path P prime does not even intersect with a supernode B. The other case is the case where I take an arbitrary augmenting path P prime in the graph G prime with a shrunk blossom, and the blossom lies somewhere on the augmenting path. And the only thing we have to realize in order to make it work, now I have to convince you that there is also an corresponding augmenting path in the original graph G when this supernode B is re-expanded, okay? And that actually works because when I walk along this augmenting path, I always have two choices. I could turn left or right. And when I turn left, in this example, I would take an even number of edges from the blossom. When I turn right, it will be an odd number of edges from the blossom. I mean, left or right could be exchanged, of course, but there is always the possibility of taking either an even number or an odd number and the right number of matching edges. So in this case, here I would have to take an even number of the edges from the blossom, and I find a corresponding augmenting path also in the original graph. It is also helpful to look at the special case where the blossom was actually a degenerate blossom of length 3. So then the augmenting path that I find could be this singleton edge, and that could be added to the matching in G prime. Okay, so P prime would be just a singleton edge here. But again, when I re-expand the corresponding blossom of size 3, I have the opportunity to take an even number of edges from the blossom and thereby obtain an augmenting path also in the original graph G. So when I have an odd length alternating path in the graph G prime with a shrunk blossom, I also find an odd length alternating path in the original graph. So there also exists an augmenting path in the original graph, and we did not create any new augmenting paths. So that was lemma 1. We are not creating new augmenting paths. And the second lemma is the other one, the more interesting one, you could say, because if there exists an M augmenting path P in the original graph, then there also exists an M prime augmenting path P prime in the graph where the blossom has been shrunk. As a matter of fact, lemma number 2 is the more interesting of these two lemmas, because this is the one that fixes our earlier problem. Our earlier problem was that we were unable to find some of the augmenting paths because of the presence of odd length cycles. And now, if there exists an M augmenting path in the original graph, and I can show that if this is the case, that there always exists an M prime augmenting path in the new graph G prime with the shrunk blossom, then I'm in shape because of the following reason. Namely, if I shrink a blossom, I'm eliminating an odd length cycle. And I may have to do that a couple of times, but of course there can only be a limited number of odd length cycles. So once at a certain point in time, I must reach a situation where there is no odd length cycles anymore. And that means our algorithm works correctly because the graph happens to be bipartite. We know that already. So it's important to realize that this second lemma is the one that fixes our earlier problem because of that reason. So let's have a look at the proof that will again be a proof by picture. Okay, so if we have, that's what we want to show, if we have an augmenting path in the original graph, which is called P, then there is also an augmenting path P prime in the graph where the blossom has been shrunk. And let's us pick the example that we had earlier, our standard blossom of length 5, and the augmenting path is sitting here. Now, the most important thing to realize is this. In constructing this alternating tree, we are entering the blossom with a matching edge, right? So that's important because then our alternating or augmenting path must leave the blossom on a non-matching edge. And hence, in the new graph where the blossom has been shrunk, this is going to be a feasible augmenting path, and this is the non-matching edge on which we left the blossom. So if there exists an augmenting path here, there also exists an augmenting path in the shrunk graph. And the re-expanding also works. So suppose I take this augmenting path and I flip matching and non-matching edges on this augmenting path, and I have the situation down here in G prime, right? So I have these two matching edges where previously I only had one on this path. And as I also indicated earlier when I explained the intuition, re-expanding this blossom, that's a blossom which has an odd length, and therefore the two matching edges that I had before are no longer feasible possibly, but I can always choose two matching edges, two other matching edges on this blossom, which I can actually take and thereby obtain the same size of the matching that I started out with here. Well, actually one matching edge more because I was using this augmenting path here. Also notice that choosing these two matching edges after the re-expansion is okay and does not create any conflict with other matching edges because this supernode B can only be incident with one matching edge. So this one is the only one, and this is the free node on the odd length cycle, and we can always choose the correspondingly other edges in order to fix in the re-expansion step again. Final picture is for the degenerate case, even though not strictly necessary, but it's maybe instructive to look at. So in the original graph, we have an augmenting path here, right? When I shrink this blossom here into one supernode B, the augmenting path will be just a singleton edge, right? That is actually an augmenting path because this was a free vertex. We started out with a free vertex, and this is also a free vertex. So both of them are free, and this one can be turned into a matching edge. And once again, re-expanding also works Now we have selected this matching edge between B and V, and the re-expansion of this blossom of size 3 also works, because here we again take the edge that is opposite of the free vertex in this cycle of length 3, and that is always feasible due to the same reason, because there is no matching edge here, and there's also no matching edge here. So that actually finishes my proof by picture, which would have been a proof on the blackboard. And I hope you forgive me if I do not write down this proof in terms of notation, but the intuition should be clear. And then the final word is going to be on the computation time of the algorithm. So let us finally have an overview of the computation time, of how I can get this computation time. So as I said, we are doing the whole business for each of the nodes of the graph. And how often could I mean, for one given root vertex of the alternating tree, how often could I shrink? Well, in each shrink operation, I at least shrink a cycle of length 3, and I make out of this cycle of length 3 one vertex only, so I'm losing 2 vertices, so I can have at most n-halves shrink operations, and afterwards also the corresponding expand operations. And if you implement that carefully with the right data structures, that still can be shown to be possible in linear time in the size of the graph, so in the total number of edges of the graph, and that is at most order n squared. Now building the alternating tree itself for one given root node, that is essentially a breadth-first search algorithm with a little bit more checks and balances, so that's also order n squared. And of course, if I find a matching path, I have to flip matching and non-matching edges along a path which can have length at most n-1 edges, so that's order n time. So without going into too many details, this is just a rough overview of the computation time estimation. I have n times order n squared plus order n squared plus order n, which is upper bounded by n to the 3. So this was a bit hand-waving in particular here, but I don't want to go into more details. You can look into the lecture notes or in a textbook if you're interested. And of course, there is better computation times possible if you do a better bookkeeping, and if you do, for example, augmenting paths along sets of shortest augmenting paths simultaneously. So you can even get the computation time down to order square root of n times m. So that finishes our analysis of the matching problem and Edmond's celebrated algorithm to compute maximum cardinality matchings in undirected graphs. So let me say that there is also a version of the algorithm where you would want to maximize the total weight of a matching if the edges also have weights. That is also possible in polynomial time, but not treated in this lecture. Instead, what we will be doing in the next lecture is looking at the generalization of the bipartite matching problem. So the bipartite matching problem was already solved earlier, so we wouldn't even need the blossom contraction business. And it has a nice interpretation, a mathematical interpretation in more general terms, namely matchings and bipartite graphs can be seen as subsets of edges which are independent in 2 matroids at the same time. And the question is, can we actually compute maximal independent sets which are independent in 2 matroids simultaneously? And the answer is yes. And that is again going to be an algorithm by whom? Of course, by Jack Edmonds. And that is the lecture or the topic of the next lecture. Thank you for your attention.